Hello everybody, be welcomed in the lecture about blood. Blood doesn't belong to body tissues because it is one of body fluids together with lymph and tissue fluid found among cells. Nevertheless, we are studying it in histology. We are studying it at the end of general histology, between general histology and microscopic anatomy. Some time ago it was given to so-called trophic connective tissues, but this concept was left, so now is blood situated somewhere between tissues and organs. As I already said, blood belongs to body fluids. So it is a fluid which is possible to study by many methods, and histology in fact isn't able to study the whole blood. It is able to study only its formed elements which represent about 40 to 50% of the whole blood content in males and only 35 to 37% in females. This difference is caused by menstrual bleeding, so these numbers are valid only during the fertile age. But isn't valid. This difference isn't valid for children or for old persons, for women after menopause. What does it mean? When we can study only formed elements in histology, we aren't able to study everything about blood plasma, representing the prevailing volume of blood. Blood plasma is the structure or the fluid which is studied by another scientific disciplines, mostly by biochemistry, immunology. So you will know many things about it during the medical studies, and here in this first lecture about blood I will say only few words about it, only some basic composition, but I will really deal with formed elements only. Formed elements are not only cells. It would be simpler to speak about blood cells, but one of three main types of formed elements aren't cells. In fact, they are only small fragments of a cytoplasm which are liberated from one very big cell situated in bone marrow. These fragments are called platelets. So blood platelets are not cells but just fragments of cytoplasm. The other two formed elements are cells, can be called cells, but the only full cells containing nuclei and cytoplasm, as you know from the general cytology, are white blood cells. White blood cells are full cells. Sometimes they can divide, sometimes not, sometimes they are terminally differentiated. Nevertheless, they have got nucleus, they have got cytoplasm, they have organelles, inclusions, cytoskeleton in cytoplasm, so everything what a real cell needs. Red blood cells are different. We still can say that they are cells, nevertheless they haven't got nuclei. They haven't got nuclei, they have only cytoplasm. They lose nuclei during their development. You will hear a second lecture about blood development, about hematopoiesis during several days. and so you will know how do they develop and when do they lose their nucleus. After that, after their full maturation, they haven't got nucleus, they have got only cytoplasm, and even more, they haven't got any organelles, they haven't got inclusions, and their cytoskeleton is reduced to so-called membrane skeleton. I will describe it later. During the whole lecture, I will demonstrate some numbers here, percents, like how many percents is the plasma content, formed elements, how many or what is the percentage of 4 elements, where is written that 99% of all formed elements are red blood cells and the remaining 1% is remaining for platelets and white blood cells together. Here at the right side there is a percentage so-called differential blood count of white blood cells. All the numbers which I will use in my lecture are the reference values from the hematological laboratory of the hospital in Motol, because hospital in Motol is the main hospital where the students of second medical faculty are going, where they are studying and where they are examining the patients. And so you will meet these values in every patient documentation, documents of patient from Motol Hospital every time contain some values from blood count, and it means you have to know all these numbers. It doesn't mean that these numbers don't vary in another laboratories, in other hospitals. Some of them are dependent on the method used in the given laboratory, and it can be sometimes different. So here in my lecture, and also during our practical trainings and also during our tests, please use these numbers which are here written, which are written in all the presentation coming from our department. And if you find another values in another sources, have on mind that it can be a result of another methodology. Several words about blood plasma. Blood plasma is a yellowish fluid containing 90% of water, 9% of organic compounds, mainly proteins, but also some low molecular compounds like sugars, glucose, amino acids, vitamins, hormones, many other things are there. And remaining almost 1%, 0.9% are inorganic salts. Salts of sodium, calcium, potassium. These are three main cations. Main anions are chlorides, phosphates. You will hear many information about the organic compounds and about the inorganic salts of blood plasma. It will be studied in biochemistry and then in many clinics. So I think that you will get all information about blood plasma, but as I already said, it isn't possible to study this fluid by any histological method, and so let's stop speak about it and let's let its description to my colleagues. Remaining volume of blood are formed blood elements. The ratio between plasma and formed blood elements is called hematocrit. Hematocrit, as I already said, is little lower in women, little higher in men. When we want to count the formed blood elements, when we want to examine blood elements and to work with so-called blood count, we need use anticoagulants like heparin or sodium citrate, etc. Because normally after collection, when sampled, blood coagulates, forms blood clot, and blood elements are trapped within the fibrin network and are not accessible for microscopic study. So before the blood sampling, there has to be prepared some anticoagulant treated tube where the blood is given and the coagulation, the clotting is stopped. If we don't stop it, and it's also used the collection of blood without hemocoagulation, we'll get blood clot and serum. Serum is a clear fluid, not so yellow as blood plasma, because it is a blood plasma without some proteins. Main of them is fibrinogen. Fibrinogen is a protein transforming during the clotting into fibrin, and after this conversion, it isn't more in the fluid, and so the serum doesn't contain it. Also, some another proteins and other clotting factors are removed from the plasma during clotting, and so the resulting serum has got little different composition than plasma. So if we want to study for example blood proteins, we have to use full blood with anticoagulants. If we want to study some low molecular amino acids and other sugars and so on, or inorganic salts, the sufficient specimen can be serum. How to work with collected blood to obtain the histologic slide. Histologic slides of blood are prepared by another method than the histologic slides for study the tissues or organs. If you want to study organ tissue, you have to prepare a tissue block and then to cut it to thin sections, and then stain and observe these thin sections. If you want to study blood under microscope, no sectioning is necessary because there isn't any solid tissue. You can prepare the slide very simply. everything you need is one microscopic glass slide and a small droplet of blood. 10 microliters of blood is enough to prepare the specimen. This droplet is given to one side of the glass. Then you need an extra glass, extra slide. You'll go with the slide towards the droplet. The blood adheres to the edge of this second glass by its capillary power, and then you'll go by this second slide under more acute angle to the other side, to the direction of this arrow, and you'll get a thin layer of blood, thin film of blood, which is called blood smear. This film is quite thick near the original droplet, but thin and good for observation at the other end. So the good place for your work and for your observation is in this circle at the second end of the glass than was the original droplet. The smear is then fixed, dried and stained, and you can look at it, you can count blood elements, this is important, you can recognize them and prepare so-called differential blood count. I will tell later what does it mean. So we have prepared blood smears for you, and you will study them in your practical trainings. So you will see how does it work. Also, the staining of blood smear is different than you know from histology, but the principle is still the same. The principle of blood smear staining is also based on the acidic and basic dyes, and acidophilia and basophilia. The staining of the blood smears is very variable. Again, each laboratory has a little another methodology. Nevertheless, words widely used is Poppenheim Panoptic method, which is using two mixtures, two solutions, May-Greenwald solution and Gimsa-Romanovsky solution. May-Greenwald solution is used as first, and that's why it contains methanol, methyl alcohol, which is here used as a fixative. And then it contains two dyes, methylene blue, which is basic dye, which stains nuclei and some granules. And the second is eosine, you know already it. It is acidic dye, it stains, for example, hemoglobin in erythrocyte, it stains another granules of white blood cells. Then, after the staining by May-Greenwald solution, the slides are washed and then stained by the second solution, Gimsa-Romanovsky, which is adding the third dye, so-called Azure B, which is oxidative product of methylene blue. That means it is originally also basic dye, but it stains mainly special azurophilic granules of white blood cells, and this staining can be sometimes important for their recognition. So these two solutions are used usually for the staining of blood smear, and this solution is connected with fixation. The whole process of blood smear preparation is quite fast and much simpler than the process of histological slides production. The first formed blood elements, which I will describe, are red blood cells or erythrocytes. Their number was already said, but I can repeat it. An adult man has usually 4 to 5.8 million of red blood cells per 1 microliter. This is equal to one quadrate millimeter. Women during the fertile age have got a little bit less erythrocytes, 3.8 to 5.2 million per microliter. The erythrocytes have got very special shape. You already know it from cytology. It is so-called biconcave shape. Biconcave means that they are flat, and both their flat surfaces have got central depression, so they are thicker near the edge than in the center. Their thickness near the edge is about 2.6 micrometers, but their thickness in the center is less than 1 micrometer. Why this biconcave shape is here found? It was counted that this shape, the structure having this shape, has got higher superficial area than the structure with the same volume but spherical shape. I am not able to explain it, but some geometrists probably can do it. So let's believe that this cell, having a usual volume 82 to 98 femtoliters, have got the wider surface area than the hypothetical cell having the same volume but spherical shape. The most important number in this slide is this one, 7.5 micrometers. 7.5 micrometers is the diameter of the erythrocyte, and you already know it. It is a number which is used during the measurement of many structures in the light microscopy, because red blood cells are found in almost all slides, because usually some vessel is present in your slide. There are very rare slides having no vessels, like for example the specimen where only cartilage or only epithelium is present, but usually you can find some vessels and so some red blood cells, and you can use them for measurement of many other structures. So please remember the diameter of the erythrocyte, and also please remember for your clinical life and for your not only clinical life, for your whole life as physician, the number of red blood cells per microliter or cubic millimeter of blood, which is very important. Red blood cells or erythrocytes are also called normocytes because their size is very stable. Sometimes you can find in a blood smear larger or smaller macro or microcyte, but if their number is higher than usually, it is a sign of some pathological condition, usually some types of anemia. You will study all these conditions in pathology. But normally we can see all the erythrocytes of the same site, so-called normocytes. They haven't got nucleus, that's I already said. Their cytoplasm is highly eosinophilic, and as they have got this special shape, when visualized directly from the flat surface, you can recognize their thicker periphery and thinner central area. Thicker periphery where the thickness of cell is more than 2 micrometers, 2.6, or thinner central area where the thickness is 0.8 micrometers. Okay, so that's why erythrocytes are usually lighter in the center than in the periphery. If not, like in this case or this case, it is because they are situated in oblique position. You can see that here that's the situation. The two erythrocytes are in one place. They are covering one the another, and that is a reason why we don't see this central lighter paler area. But if the erythrocyte is alone, and if it is sticked to the slide by its whole diameter, you can see the lighter central area where, as we know, the cell is thinner. The shape of erythrocytes is much nicer when visualized by scanning electron microscope. Here we can see three-dimensional picture, and so really biconcave shape is visible. The erythrocytes here resemble donuts, but the hole in the center isn't complete. It's just thinner part of the cell, but not the real hole like a donut has got. If you observe the erythrocyte in the transmission electron microscope, you have to use sectioning. Erythrocyte is too thick to be visualized well under the transmission electron microscope. So if you want to study not only erythrocyte, all blood elements in the electron microscope, you have to centrifuge them, and the pellet made by this centrifugation is then embedded like a tissue and sectioned by ultramicrotom. So the result are sections of blood cells, in this case of red blood cells, and the resulting shape depends on the place where our erythrocyte is cut. So for example, this one and this one are well cut through the center, and so we can see thinner central area and thicker periphery. The picture resembles biscuits. On the other hand, this one is sectioned only through this thicker rim, so we don't see the typical shape. The second thing which we can see is the electron dense inner content of the erythrocyte. We can see that the inner content is quite homogeneous. There aren't any structures, there aren't any granules, organelles or something like this. There is just black material, electron dense material. This electron density is to some level natural feature of erythrocytes, because, as I will say in a moment, the main proteins of the erythrocyte cytoplasm is hemoglobin, and hemoglobin is a protein having iron in its molecule. Iron belongs to metals, and electron density is dependent on the presence of metal elements. So erythrocytes and their hemoglobin are naturally electron dense, in fact. As we saw, erythrocytes don't contain any organelles, any inclusions, and as I already said, they don't contain any typical cytoskeleton. The only elements which can be said that resemble cytoskeleton is so-called membrane skeleton. Membrane skeleton isn't a real cytoskeleton because all its filaments and proteins are connected to the plasma membrane of the erythrocyte, and so all of them belong to integral or peripheral membrane proteins, and so all the elements of the membrane skeleton in fact belong to composition of a plasma membrane of the erythrocyte. Plasma membrane of the erythrocyte is very well understood because it's possible to obtain it relatively pure, but together with membrane skeleton after hemolysis of erythrocytes. So plasma membrane of erythrocyte was understood very, very early in the middle of the 20th century. Its composition was well known. It was used for the chemical study, biochemical study of the membrane composition. According to the composition of erythrocyte membrane, we recognized a long time ago that the membrane is composed of phospholipids, cholesterol, proteins, but there wasn't clear how all these molecules are connected together. But the chemical composition of the membrane was known, as I said, quite early. Now we know composition of a membrane, and we know that the membrane of erythrocyte is containing many proteins. Some of them belong to this membrane skeleton, mostly these which are in this schema. Band-3 and glycophorin C are integral membrane proteins, which are penetrated integral membrane proteins, which are firmly embedded in a membrane and which are working as anchorage places for the whole skeleton. Band-3 binds another protein now belonging to peripheral membrane proteins, which is called ankyrin. Through this ankyrin, probably the most important protein of the membrane skeleton is joined to membrane, and it is called spectrin. Here it is written. Spectrin is the main protein of the membrane skeleton. It is a fibrillar protein forming naturally dimers. These dimers join together end to end and form tetramers. And these tetramers are connecting together in the area of so-called junctional complex. This junctional complex doesn't only join tetramers of spectrin, but also connects this whole network to the plasma membrane through the glycophorin C. Junctional complex is a really complex structure having thin actin microfilament in the center. It's quite short, but typically composed of double helix of actin, and additional tropomyosin is here connected, so it slightly resembles thin myofilament, which you know from muscle tissue. And really, myosin molecules which are soluble, which are soluted in the cytoplasm of the erythrocytes, can bind it and can be responsible for the special shape of erythrocytes. So this shape of erythrocytes isn't automatic, it is a result of the work of actin and myosin and other additional proteins compounds in the membrane skeleton. So the erythrocytes needs energy to maintain its shape. When it loses energy, when it becomes older, the shape isn't more maintained. Erythrocytes become still more and more spherical, and it is one of the signals for macrophages to phagocytose them and to finish their lifespan. Membrane skeleton is the only thing which we can see in the electron microscope using some special techniques. So here we can see a picture from the transmission electron microscope, but it isn't section, it is so-called a replica specimen, and here is a junctional complex, and these are tetramers of spectrine. In this case 1, 2, 3, 4, 5, 6, 7 tetramers are connected by one junctional complex having actin filament with tropomyosin and so on. On the other side, here in this place where two dimers of spectrine are connected, the tetramers are connected with the membrane by band 3 protein, and all these proteins forming the membrane skeleton are important mainly for the shape of the erythrocytes. Proteins of the membrane skeleton aren't the only membrane proteins in the erythrocytes membrane. There must be some another, like ion channels, for example, glucose transporters, because the erythrocyte is dependent on anaerobic glycolysis, and also special, usually integral membrane proteins of blood groups. You hopefully know what blood groups are. There doesn't exist only well-known ABO system, which is based on the variability of special glycans, special sugars on the glycolipids, but there is also RH system, well known. Maybe somebody of you, maybe somebody of you can know also. Pardon, I have to delete all drawings, and now it's maybe better. So RH system is well known, MN system is well known, but there are several other blood groups. You will study them in hematology, and these are usually given by variability of integral membrane proteins or glycoproteins. I already said that the cytoplasm of erythrocytes is containing hemoglobin. In fact, hemoglobin represents between 32 to 36% of erythrocyte volume, so quite a lot. It's possible to say that the cytoplasm of erythrocyte is 32 to 36% solution of hemoglobin, because nothing more, almost nothing more is inside. Each hemoglobin molecule is composed of 4 chains of globin, which is a protein, and form prosthetic groups, which are called hemes, and each of them has got a ferrous ion. Globin chains are quite variable. These are proteins which are quite variable, but in adults the most frequent is hemoglobin A, having 2A and 2B chains of globin. There exists also less frequent A2 chain, where 2B chains are replaced by 2D chains, and adult blood, adult erythrocyte has got also fetal hemoglobin, where are 2G chains instead of B chain. Of course, fetal hemoglobin is much more present in fetus and small children, because it has a little higher, not little, it has higher capacity to bind oxygen, and it is the main function of hemoglobin. It is a complex protein which can bind oxygen. When hemoglobin is binding the oxygen molecule, it is then called oxyhemoglobin. It binds oxygen in the organs where its level is higher. That means in adulthood in lungs, during the embryonic and fetal development in placenta. Then it releases oxygen after the drop of its environmental concentration. That means when the erythrocyte comes to some tissue, and on the other side it binds carbon dioxide in the tissue. If the carbon dioxide is bound to hemoglobin, then hemoglobin is called carb aminohemoglobin, because carbon dioxide doesn't bind to heme prosthetic group but to amino groups of hemoglobin amino acids. But carbon dioxide can bind also to blood plasma, so carbon dioxide is not so much dependent on the presence of erythrocytes. Its transport is not so dependent, but transport of oxygen is dependent on erythrocytes and on hemoglobin. The bond of oxygen and hemoglobin can be irreversibly blocked by the bond of carbon monoxide, very dangerous toxic gas, which when bound to hemoglobin prevents its oxygenation. The hemoglobin with carbon monoxide is then called carboxyhemoglobin, and hemoglobin can also be oxidized, mainly by the presence of NO2 solutions, NO2 compounds, and the result is methemoglobin, which also doesn't bind oxygen well. This situation can happen mainly in small children when fed by food with a high content of nitrogen compounds. quite important number is level of hemoglobin in blood. Of course, it is dependent on the number of erythrocytes, so it must be higher in men than in women, and also the amount of hemoglobin in one erythrocyte, which is measured in picograms. This is the model of the hemoglobin molecule and model of its prosthetic heme. Iron is found in each heme, and hemoglobin has got 4 such groups. During the development, the red blood cell loses its nucleus, loses all organelles, but sometimes we can find even in peripheral blood after the full development some remnants of nucleus in the erythrocyte. If they look like a ring, which is here visible, we can call it Cabot ring. Sometimes small bodies are found, of course, basophilic bodies are found in erythrocyte. This is then called Howell-Jolly body. If we find a low number of such bodies of rings, it can be a random finding without any clinical significance, but high amounts of such nuclear remnants can be a sign of some pathology. Erythrocytes can live usually 4 months, that means 120 days. After this time they die because they lose their ability to maintain the size, their flexibility is worsened, membrane transport is lower, everything is dependent on their energical metabolism. Energical metabolism of erythrocytes is dependent of anaerobic glycolysis. It is a paradox situation that the cell which is transporting oxygen cannot use it, but having no mitochondria, erythrocytes really cannot metabolize oxygen, cannot use it for oxygenation, for oxidative metabolism, and so it is dependent on anaerobic, unoxidative metabolism, mostly of glucose. And of course, erythrocytes having no nucleus and so no ability of proteosynthesis cannot produce new enzymes of this glycolytic metabolism. So after exhaustion of all enzymes, energetical situation becomes worsened, and the whole chain of events is starting, leading to their death. For example, oligosaccharide chains are exposed on the surface. Phosphatidylserine, one of typical inner leaf phospholipid of the plasma membrane, is transported to the outer membrane, and all these things are recognized by macrophages, mainly in spleen but also in liver, in lungs, and erythrocytes are phagocytosed, and their iron and other important components can be recycled and used once more. So that's everything what I wanted to say about erythrocytes, and now let's go to white blood cells or leukocytes. It is a whole family of cells, very heterogeneous. Together 5 types of white blood cells exist. They are full cells, they have nucleus, they have organelles, they have inclusions, they have cytoskeleton, they represent about 4,000 to 10,000 elements per 1 microliter of blood. So if you compare this number and number of red blood cells, there is about 500 times less white blood cells than red blood cells. So this difference is enormous. The white blood count isn't a value which is representing the whole number of white blood cells in vessels, because they express special membrane ligands for ENP selectins. These selectins are cell adhesion molecules which are found in endothelial cells, in the membrane of endothelial cells. You probably already know that endothelial cells are special cells which are lining vessels, and so endothelial cells can bind white blood cells. It was counted that probably the same number of white blood cells which is dispersed in bloodstream is bound to endothelial cells, and these bound white blood cells represent so-called marginal pool of white blood cells, which means that in fact at least 2 times more white blood cells are situated in a vascular system than we are able to count in blood smears. White blood cells can roll on the inner surface of vessel wall, and they can penetrate through the vessel wall by 2 processes which are called diapedesis and emperipoiesis. Diapedesis means penetration of white blood cells through very narrow spaces between endothelial cells. Emperipoiesis is a very sophisticated method how white blood cells can penetrate through the endothelial cells. So they can penetrate between endothelial cells and through the endothelial cells. Both these processes are directed by many chemical signals, signal molecules, which are diffusing through the endothelium, and white blood cells can recognize them, and white blood cells are attracted to them. This attraction by chemical signals is called chemotaxis, and it is a motor of diapedesis or emperipoiesis of white blood cells through the vascular wall. Of course, they can penetrate through the wall of very small, thin vessels like capillaries, and also special postcapillary venules are equipped by the specializations important for these diapedesis and emperipoiesis, that means for the penetration. The main place of leukocyte function is in the tissue outside the bloodstream. They are just transported by blood, but they start to work and they start to fully express their genome and start fully develop after the leaving the blood and entering the tissue. It can be connective tissue usually, but they also can enter nerve tissue, they can enter muscle tissue, not so much epithelial tissue because it is avascular. If some white blood cells penetrate to the epithelium, it can do it through the basement membrane, but not directly by diapedesis or emperipoiesis. And there in tissues, mainly in the connective tissue, is the place where white blood cells are working. They are working mainly in defense of the organism. They are working in phagocytosis. They are working in the immunity. Their function are very variable. As I already said, there exist 5 types of white blood cells, and we can divide them into 2 groups. 2 groups are called granulocytes and agranulocytes. Granulocytes have got specific granules in their cytoplasm. Specific granules. Agranulocytes haven't got them, so I write here specific granules minus. So granulocytes have got specific granules, agranulocytes haven't got any specific granules. But there exist also azurophilic granules. Azurophilic granules which are stained by azure, one of dyes used during Poppenheim's staining, and they are present in both groups, that means in all 5 leukocytes. So the term agranulocyte doesn't mean that the cell hasn't got any granules. It means that the cell hasn't got specific granules, but azurophilic granules can be found there. So azurophilic granules are in all leukocytes. The second thing how to recognize granulocytes and agranulocytes is the structure of the nucleus. When you look at these pictures, you can see that granulocytes have got much more irregular and complicated nuclei than agranulocyte. Mostly these 2 first granulocytes have got typical segmented nuclei, which means that their nuclei are divided into several segments. Here are 3 segments, here are 2 segments, which are connected by thin chromatin bridges. So it is still one nucleus, only specifically segmented. Less segmentation in this last type of granulocyte, but sometimes nucleus of these basophilic granulocyte can be segmented as well. This very, very specific shape of the nucleus this is why granulocytes are also called polymorphonuclear leukocytes. H should be here. Polymorphonuclear, very long word. Polymorphonuclear leukocytes. So the first group can be called granulocytes or polymorphonuclear leukocytes. Agranulocytes have got simpler nuclei. They can be usually spherical or kidney shape, ovoid, sometimes lobated, but never segmented. Due to this simpler shape, simpler microscopic picture of nuclei, Agranulocytes can be also called mononuclear leukocyte, mononuclear white blood cells, which doesn't mean mononuclear leukocyte, which doesn't mean that they have got one nucleus. All leukocytes have got one nucleus, but it means that their nucleus is simpler, has got one segment only. Yeah? So there are granulocytes or polymorphonuclear leukocytes and agranulocytes or mononuclear leukocytes. Maybe you know a disease called mononucleosis. It is a disease where high amount of mononuclear leukocytes or agranulocytes is in blood count, so it is called according to this feature. We have to classify the white blood cells more. So not only these two groups are here, but there are also members of these groups. Members of granulocytes are classified according to staining features of their specific granules. Their specific granules can be sometimes eosinophilic, sometimes basophilic, and sometimes, let's say, something between eosinophilia and basophilia, and these granules and granulocytes are called neutrophilic. So we are distinguishing neutrophilic, eosinophilic and basophilic granulocytes according to staining of their granules, specific granules. Because azurophilic granules stained by azure, and it is the same in all white blood cells. You can read here also some numbers. One of them is a size, so you can see that they can be quite variable, but all granulocytes can measure something between 10 and 14 micrometers. So let's say they are a little bigger than red blood cells, or they can reach a size of 2 red blood cells. Maybe more important for the physician is this percentage. This percentage means how many, or what is the percentage of this particular type of white blood cells in the whole number of white blood cells. So you can see that the most frequent white blood cells are neutrophilic granulocytes. On the other side, the rarest white blood cells are basophilic granulocytes. Agranulocytes are of two types only. One of them are lymphocytes, which are very small, usually, not every time, but usually very small white blood cells, smallest white blood cells, which have a diameter almost the same as red blood cells. And the second extreme are monocytes, which are the biggest white blood cells, which can reach 200 or more micrometers, so let's say like 3 erythrocytes. Also, their numbers are quite stable. Lymphocytes are the second most frequent white blood cells. Monocytes belong to less frequent white blood cells together with eosinophilic granulocytes. Their number can be usually equal. So that's the types of white blood cells, the numbers or percentage of white blood cells, size of white blood cells, classification of white blood cells. So now let's look at particular types. Let's start with granulocytes. As you know already, there are neutrophilic, eosinophilic and basophilic granulocytes. All of them have a very special nuclei. The highest level of segmentation is usually found in the neutrophilic granulocytes, which can contain, or the nucleus of them can contain 2, 3, 4, 5 segments, sometimes even more, but in this case it is so-called hypersegmentation of a nucleus. As eosinophilic granulocytes have got less segmented nucleus, and which means that usually 2 segments are here, and nucleus, the most typical picture of the eosinophilic nucleus is like a glass. Basophilic granulocytes haven't so much segmented nucleus. Their nuclei have usually shape of a letter S or some slight segmentation, and the problem here is also that they have many basophilic granules which are so darkly basophilic that nucleus is not well visible in the cell when visualized in smear, because these granules are overlapping the nucleus, and so we don't see it very well. But nucleus isn't the only difference. Maybe the main difference of these granulocytes is staining and character of granules. You can see in this picture that not only staining but also the size of granules are variable. Neutrophilic granules are very small. They are just at the verge of the resolution power of light microscope, so we don't see them very well in smears. We have to use the highest magnification, and we will use the highest magnification in our practical class, so you will see them, but you will see that they are not very well visible. On the other hand, eosinophilic and basophilic granules are coarse, large. They measure 1-2 micrometers at least, and so they are clearly visible even in smaller magnifications. And of course there is a different staining of these granules. All the granulocytes can contain also azurophilic granules, which we don't see in this drawing, but which we will see in a microscope. Neutrophilic granulocyte has a size something between 10-12 micrometers, so bigger than an erythrocyte. You can see it. You can see segmented nucleus. In this case, we can count 4 segments of the nucleus, and they are connected by bridges, chromatin bridges, but they are connected, so the cell doesn't contain 4 nuclei, it's 1 nucleus. And in this high magnification you can see granules. There are very many, and some of them are darker purple, and they are azurophilic granules. We can count segments of the nucleus, because it was discovered that the older is the neutrophilic granulocyte, the more segments has got its nucleus. The youngest neutrophils have got unsegmented nucleus, or their nucleus is just beginning its segmentation. These are called band cells, or simply bands. On the other hand, the oldest neutrophils have got hypersegmented nucleus with more than 5 segments. Usually in 41% we can find 3 segments of a nucleus. That's the typical picture, 3 segments of a nucleus. Here is a band, very young cell, very young neutrophilic granulocyte, which just probably left the bone marrow and is only for a short time in bloodstream. If there is a number less than 5% in peripheral blood, number of these cells less than 5%, it doesn't mean anything pathological, but if there is a higher number, it's a sign of higher frequency of neutrophilic formation, maturation, which can be a sign of pathology, mostly of some bacterial infection. Here is typical hypersegmentic neutrophilic, which is very old, and again their high number can be some pathological sign. Barr's body, it is an interesting structure which is found in about 3% of neutrophils of females. Only in females the Barr's body is found. It was discovered that there is one inactivated X chromosome in this part of a nucleus, forming this short appendix situated in one of the nuclear segments. So there is possible to recognize the gender of the patient according white blood cells, and particularly according to Barr's bodies in the neutrophilic granulocyte. What is the electromicroscopic picture? Of course, when we prepare a specimen for the electron microscopy, we have to cut white blood cell or all blood cells. I already said how do we prepare the specimens, and so we interrupt the chromatin bridges, so it seems that the cell has got more nuclei, but each of these nuclei is in fact one segment of a nucleus. You can see normal organelles, as usually Golgi complex is very well visible, or Golgi apparatus. What can be recognized? Some rough endoplasmic reticulum is here. Of course, mitochondria are here or here. And what is the most prominent are these electron-dense structures, and they are azurophilic granules. Azurophilic granules in the electron microscope are electron-dense, and this is because they contain a lot of lysosomal enzymes, and you know already that lysosomal transport vesicles, which contain the same enzymes, are highly electron dense. The only difference is that azurophilic granules are bigger than lysosomal transport vesicles. Lysosomal transport vesicles measure usually less than 100 nanometers. On the other hand, azurophilic granules can measure more than 1 micrometer. They can be clearly visible in the light microscope. So we can say that azurophilic granules of all leukocytes are large, extremely large lysosomal transport vesicles. Specific granules are smaller. They can be also spherical, but their shape can be variable. We can find also rod-shaped specific granules. Their content is electron lucent, almost lucent, or very, very slightly electron dense only. And so they are less prominent in the cytoplasm, but if you look at the picture carefully, you can see that their number is high, and their number is higher than the number of bigger and dark azurophilic granules. So there are specific granules, azurophilic granules, organelles. We don't see anything more here, but we can be sure that we would find all the typical components of the eukaryotic cell. What is the content of granules? I already said that azurophilic granules contain lysosomal enzymes, but in neutrophilic granulocytes. The azurophilic granules are a little different than in the other two granulocytes, where only lysosomal enzymes are there present. Here in neutrophils there are also another enzymes, and among them I would prefer myeloperoxidase. Myeloperoxidase is an enzyme which is very specific for the neutrophils, which is typically present in their azurophilic granules and which can serve as a histochemical marker for not only mature granulocytes. It isn't usually necessary to use histochemistry for recognition of mature granulocytes because they are easy recognizable, but also developing neutrophils, their precursors should contain myeloperoxidase, and their recognition is not so easy, so the histochemistry can be used there and sometimes is used because sometimes it is important to recognize them in some leukemias and so on. So azurophilic granules of neutrophils contain not only lysosomal enzymes but also some additional enzymes. Specific granules of neutrophils contain enzymes which are important for the function of them, like lactoferrin, lysosine, phagocytins. All these are enzymes which are specialized for killing bacteria and killing the fight against bacteria. It is the main function of neutrophilic granulocyte. They also contain these specific granules also contain some proteins important for penetration through the connective tissue, for the penetration through the membrane, and some activators of immune processes in the tissue. But these bacteriocytic or bacteriostatic enzymes are the most important. It was discovered recently that neutrophilic granules should contain also tertiary granules. Neutrophilic granulocytes should contain also tertiary granules. Their morphology isn't clear, but we know that they contain another enzymes than two previously mentioned granules, and they are mainly important for the penetration of neutrophilic granulocyte through the extracellular matrix of connective tissue. Mainly metalloproteinases are important enzyme for the extracellular matrix cleavage. This is another picture of the neutrophilic granulocyte in the electron microscope, and we can see special processes on its surface. These white processes are called pseudopodia, and they are important for diapedesis, for penetration of the white blood cell through the vessel wall, and also for further movement of the cell through the extracellular matrix. These pseudopodia are supported by microfilaments only. Microfilaments are movable when cooperating with myosin, you already know it, and this is the mechanism allowing the movement of these cells through the connective tissue. The schema here is describing the function of the neutrophilic granulocyte. As I already said, the main function is the phagocytosis and killing the bacteria. So the beginning is that the white blood cells recognizes and incorporates bacterium. Bacterium is then found in the heterophagosome. Heterophagosome is then fusing with a specific granule, which means that the bacteriocytic or bacteriostatic enzymes are coming to the contact with the bacterium, and they try, and usually successfully try, to kill it. So they kill bacteria. Bacterium then is not more dangerous. The complex of phagosome and neutrophilic specific granules then fuses with azurophilic granule, which brings another enzymes, mostly lysosomal enzymes. The result is lysosomal digestion, and the cell can recycle and reuse some components of bacteria, some sugars or proteins, amino acids, and what is remaining can be stored as the residual body. The neutrophils don't live very long. After this bacterial phagocytosis, they usually die during several hours or days, and the masses of dead leukocytes then become a pus, which is visible in the places of some massive bacterial infections. Eosinophilic granulocytes are a little bigger, less frequent. They represent less than 5% of all leukocytes. Their nucleus has usually 2 segments. Nevertheless, in this photograph we can see 3 segments. It can happen, but as I already said and showed in the picture, usually 2 segments of nucleus is typical. We can see their specific granules even in a small magnification. They are very highly eosinophilic. They are more eosinophilic than red blood cells. You can compare the color of red blood cells and granules of this our granulocyte. The typical color of eosinophilic granules is brick-like, but sometimes you will see it in our smears. It doesn't resemble brick so much. They can be more purple. Nevertheless, typical color repeated in textbook and visible also in this picture is like brick. Eosinophilic granulocytes are similar functionally and also morphologically to neutrophilic granulocyte. Here you can see mostly 2 segments, but their granules are different in the electron microscope. Their specific granules are not only bigger, but they have also very regular, usually lens-like shape, and we can see, here it is very visible, we can see darker, more electron dense crystalloid in the center of, let's say, moderately electron dense granule. So that this crystalloid in the granule is so typical that we can recognize eosinophilic granulocytes in the electron or microscopic pictures. Granules of specific granules of the eosinophilic granulocytes contain many proteins. All of them are again enzymes, and we can divide these enzymes into 2 groups. One of them, which are these 4 here, these 4 enzymes are enzymes which are important for killing and digestion of parasites. So the fight against parasites, which can be unicellular, like protozoa, like Leishmania or Trypanosoma. This is a similar process as I already described in neutrophilic function. The eosinophilic granulocytes can phagocytose this unicellular parasite. Proteins of specific granules can kill it, and lysosomal enzymes of Azurophilic granules then digest them. But there exists also larger parasites which is impossible to phagocytose, mostly worms, Taenia or Oxyuris. So it means that eosinophilic granulocytes can also secrete their enzymes. They can secrete content of their granules and they kill the parasitic worm extracellularly, and then maybe phagocytose its remnants. So this is the first important function, antiparasite function. But granules of the eosinophilic granules can contain also another enzymes, aryl sulfatase and histaminase, which are important for the reduction of inflammatory changes in the tissue. So eosinophilic granulocytes are also anti-inflammatory cells, and this function is important mostly in allergic reactions where number of eosinophils is increasing and their work is reducing the allergic inflammation. So their work is positive for the patient. Their higher number there is a positive sign that the patient is able to fight against its allergic reaction. Once more, higher magnification of eosinophilic granules in the electron microscope. So typical picture, please remember this picture because it is possible to recognize eosinophilic granules in the electron microscope very easy and quickly. Basophilic granulocytes are very rare cells. They represent less than 2% of leukocyte, but very frequently we don't find them in the specimen. They are the smallest granulocytes, around 10 micrometers, and as I already said, they big and dark basophilic granules can cover the nucleus, so the nucleus is not well visible. You can see it, or in fact you don't see the nucleus very well in these cells, but believe that it is there situated under the granules. In the electron microscope we can see 2 or 3 sections of a nucleus here. 1, 2, 3. By the way, there is very typical the peripheral heterochromatin, not only for basophilic granulocyte, but for all 3 types of granulocyte is typical the peripheral arrangement of heterochromatin and central euchromatin in the segment. And the second thing which you can see here are big granules. They are really very big. They measure several micrometers. They are irregular in shape but have got a membrane on the surface. They are highly electron dense and of course basophilic in the light microscope. Instead of them you can see mitochondria here, Golgi complex here, rough endoplasmic reticulum here, also normal organelles as usually. Another picture showing irregular basophilic granules. Sometimes you can see something called myelin figures in these granules, which means lamellarly arranged electron dense structures. Specific granules of basophilic granulocyte don't contain only enzymes. Some enzymes are there, but there are also low molecular substances like heparin, histamine, chondroitin sulfate. Some of them, mainly heparin and histamine, but also eosinophilic chemotactic factor and slow reaction or substance of anaphylaxis, all of them are pro-inflammatory substances. So basophilic granulocyte work work in the opposite mode than eosinophilic granulocyte. They increase inflammation. Histamine is increasing vasodilatation and transudation of fluid through the vascular wall. Heparin is anticoagulant factor, so it prevents blood coagulation, and so it can again increase transudation of fluid through the inflammatory changed vessels. So basophilic granulocytes are pro-inflammatory cells. They also increase in number in places of inflammation, but their function is opposite than the function of eosinophils. Now let's go to agranulocytes or mononuclear leukocytes. More frequent are lymphocytes. They represent the second group of white blood cells in size, 20 to 45%. In children, they are more frequent than neutrophils. Some equilibrium in the number of lymphocytes and neutrophils is coming around the 8th year, and the older children and adults have got more neutrophils than lymphocytes. They are quite small cells, usually they measure something like erythrocyte. Their nucleus is very dark, darker than in other white blood cells. Mostly heterochromatin is there, and the shape of nucleus is usually spherical, or sometimes it can contain small depression, small indentation. Here it isn't visible, but it will be visible in another picture. So nucleus can be spherical or indented. If the lymphocyte is so small, like in this left picture, about 6 to 8 micrometers, it has very low amount of cytoplasm. Its cytoplasm is then like very thin rim around the big central nucleus. Oh no, I don't want to. Oh, sorry, but let's, yeah, okay. Relatively large and dark nucleus, small amount of cytoplasm. The cytoplasm of lymphocyte is basophilic, more basophilic than in other white blood cells, and it doesn't contain any specific granules, so it can be like homogeneous, but sometimes azurophilic granules are found there. Lymphocytes, when activated, can be bigger, so we can classify them as small, moderate, and large. This right picture is a moderate lymphocyte. You can see that nucleus is still of the same size, but it has more cytoplasm, and this cytoplasm is not so much homogeneous as was in this left one. More azurophilic granules is here forming. It is a sign of the lymphocyte activation. When fully activated, the lymphocyte can reach 18 micrometers, so it can be at least 2 times bigger than at the beginning of its activation. So it is the case of so-called large lymphocyte. Of course, the larger is lymphocyte, the lighter and bigger is its nucleus. It's the activation of the nucleus is of course bringing more euchromatin, because the activation is towards the cell which is producing and later also secreting more proteins. If we look at the lymphocyte in the electron microscope, we can see, for example, here this already mentioned indentation of the nucleus. We can see mostly heterochromatin cytoplasm. It contains many ribosomes. This is why it is so much basophilic. These ribosomes can be free, but also, as for example here, bound to membranes of rough endoplasmic reticulum, and so the cell has to contain also Golgi complex. Of course, mitochondria have to be present. It is necessary for every cell with the exception of erythrocyte, and lysosomal transport vesicles forming already known Azurophilic granules. Another picture, little higher magnification but smaller lymphocyte and Azurophilic granules are here well visible. Sometimes their number is higher, sometimes lower. It depends on the type and on the level of activation. Because the lymphocytes are not classified only simply into small, medium and large, but we know another classification, much more important. We will speak about lymphocytes and their classification in the lymphoid system as well, and you will study them once more in immunology and once more in pathology. So now really very briefly to the second very important classification of lymphocyte. The basic classification of lymphocyte is according to places of maturation, or better said, places where they acquire their immunocompetency. Some lymphocytes, or all lymphocytes, come from hemopoietic organ, which is in adults bone marrow. In adult people, only bone marrow can contain lymphoblasts. Lymphoblasts are young precursor cells which are dividing and which give rise to daughter cells which can differentiate into lymphocytes. You will hear about the lymphopoiesis in the next lecture. Lymphocytes, when developed but still not fully mature, can then leave a bone marrow and occupy one very important lymphatic organ which is called thymus. These lymphocytes, which acquire their immunocompetency or which become mature in the thymus, are then called T lymphocytes. Or the lymphocytes don't leave bone marrow, they stay here, or they leave it and go to some secondary lymphoid organs. You will hear about them early in the lecture about lymphoid tissue. And this population of lymphocytes, which is less frequent, becomes so-called B lymphocytes. So we have already T lymphocytes and B lymphocytes. T lymphocytes are maturing in thymus, B lymphocytes in bone marrow or secondary lymphoid organs. They are called B lymphocytes according to special primary lymphatic organ of birds, which is called bursa of Fabricius. Bursa of Fabricius is a special diverticle of the intestine in birds, where B lymphocytes of birds acquire their immunocompetency, but mammals haven't got it. Nevertheless, their lymphocytes of the same type preserved the name B lymphocytes. So B, T, and the third group of lymphocytes, less frequent, is natural killer lymphocyte, or frequently called natural killer cells. They develop also in bone marrow, but in fact they don't acquire immunocompetency because they have got immunocompetency from the beginning. They are members of so-called innate immune system. Innate immune system means that their immunity competency is natural. It isn't necessary to teach them to recognize to recognize the cell which should be affected by their releases. So they naturally recognize some cells, I will say which cells, and kill them by lysis. On the other hand, T lymphocytes, some T lymphocytes can do the same function. They also can destroy some damaged or infected cell, but they have to teach it. It isn't their natural ability. So-called cytotoxic T lymphocytes represent the main effector cells of the adaptive immune system, adaptive cellular immunity. So we have innate immune system and adaptive immune system. Innate immune system, it has effector cells in natural killer cells. Also there exists humoral innate immune system. It is, for example, complement and other complexes of plasma proteins. And then we have got more sophisticated and phylogenetically younger adaptive immune system, which has got cellular effector cells, so-called cytotoxic T lymphocytes, one from the group of T lymphocytes, and there also exists adaptive humoral system. I will show it in the next picture. Humoral immune system, adaptive humoral immune system, is a system which is based on the function of B lymphocytes. B lymphocytes, which are maturing mostly in bone marrow, have got special receptors on their surface which can recognize some foreign molecules. These foreign molecules can be really foreign, like microorganisms, bacteria, but sometimes there can be also self molecules which are transformed. This recognition of the foreign material is leading to series of mitoses. During this mitosis, the B lymphocytes are changing, they're improving their ability to bind antigen, and the result of this series of mitoses, which will be more described in lymphatic system and even more in immunology, the result is formation of effector cells of humoral adaptive system, which are your already known plasma cells. Plasma cells are effector cells of adaptive humoral immunity. They are daughter cells of B lymphocytes. They are secreting antibodies, and these antibodies can bind to the same antigens as were these which provoked at the beginning the activation of B lymphocytes, and these antibodies then neutralize the antigens. Antigens can be then phagocytosed by macrophages, or some another fate of antigens can be, but antibodies in every case can bind to their surfaces. And antibodies are products of plasma cells, and plasma cells are daughter cells of activated B lymphocytes. Some B lymphocytes don't change to plasma cells but remain in blood or in secondary lymphoid organs like memory cells, prepared for next activation by the same antigen, and this second activation is much faster because they are already activated, they are just sleeping. Cellular acquired immune system is based on T lymphocytes. The system of T lymphocytes is quite complicated. I will show it once more. T lymphocytes, sorry, I only delete drawings, these previous drawings here. T lymphocytes can further differentiate into 4 groups. The first of them is cytotoxic T lymphocyte. The second important and second frequent is helper T lymphocyte. The third important is regulatory T lymphocyte. And the fourth and least understood is so-called natural killer T lymphocytes, or other not so well specified T lymphocytes. I will speak only about cytotoxic, helper and regulatory T lymphocytes today. Or T lymphocytes can be immunohistochemically recognized according to surface marker CD3. These CD markers, CD, it doesn't mean compact disc, it means cluster of differentiation. Cluster of differentiation. These are special integral membrane proteins which are very specifically expressed on variable cell types, and they are used for recognition, differentiation. They are used for recognition of white blood cells mostly, but also another cells. Almost all cells have got them. There are plenty of CD molecules, but only few of them are important for us at this moment. So maybe you can remember that all T lymphocytes are recognizable according to CD3, but then the subtypes of T lymphocytes have also some additional CDs. The cytotoxic lymphocytes, which I have here under the number 1, have every time CD8 together with CD3. Helper T lymphocyte have got CD4. Little complicated is situation in a regulatory lymphocyte, which can contain CD4 or CD3, but much more specific for them is CD25 and also so-called FOXP3. By the way, B lymphocytes are also recognizable according to CD20 or 23. NK cells are also recognizable according to CD16 or 56. And as I already said, there are many other CDs, and we are using them in laboratory for recognition of cells, of mostly of blood cells, but also macrophages and endothelial cells and so on. So, cytotoxic T lymphocytes are effector cells of adaptive cellular immunity. When activated, they can recognize, bind, and destroy some cell which is either infected or also tumor transformed. On the other hand, helper T lymphocytes doesn't destroy anything, it is activating. Helper T lymphocytes can also recognize some antigen, but the result of this recognition of this bond is secretion of proteins from group of cytokines which activate, for example, B lymphocytes or macrophages and also another white blood cells. Regulatory T lymphocytes, they are important for the regulation of the immune answer. They little bit reduce the rate of bonds between white blood cells, and they tend to reduce mostly autoimmune reaction of the organism. Sorry, once more, sorry. T helper cells, just shortly. This schema can show how do they work. T helper cells, they can recognize a cell which is binding an antigen, that means some foreign molecule, together with MHC2 complex. MHC2 complex is so-called main histocompatibility complex. MHC means main histocompatibility complex. Complex. It is a complex which is found on every cell, but there exists MHC1 and 2, and this MHC2 is not in every cell, but it is only on the cells which can recognize antigens which are processed by lysosomal digestion. That means the cell, like macrophage for example, can phagocytose some antigen, process it by lysosomal digestion, and then present its part with the antigenous function on the surface. This complex of antigen and MHC is recognized by T helper lymphocyte, and after this activation, T helper lymphocyte secretes some cytokines, for example interleukin in this case, and it can activate another cells. There are 4 groups of T helpers, and each of them can activate another cells. Th1 can activate macrophages, Th2 eosinophils and basophils, Th17 neutrophilic granulocytes, and THF, so-called follicular T helper, can activate B lymphocytes. So this helper in this picture is probably this F type. it activates B lymphocytes, and B lymphocytes have then ability to bind their antigen and to transform into plasma cells or memory cells. So this is the function of helpers. Each of them has got another cytokine like interferon gamma, interleukin 4 or 13 and so on. I already said something about the killers. They recognize and bind cells where are MHC1 complexes and some bound antigen. MHC1 is the complex which is on every cell, not only on antigen presenting cell like was the macrophage in the previous picture. So MHC1 and antigen can be found on every cell. This cell can be recognized by T cytotoxic lymphocytes, which were some time ago called killer cells, but now we rather use the name cytotoxic T lymphocyte. And this recognized cell can be directly destroyed. And one picture concerning T regulatory lymphocyte. There exist natural and induced Tregs, and both of them are important for inhibition or suppression of immune responses. And the picture about the natural killer cells. Natural killer cells don't belong to B or T group of lymphocytes. It is special group of lymphocytes. They are developing in bone marrow, and they have an innate ability to recognize and then kill any cell having incorrectly or insufficiently expressed MHC1. So NK cell, natural killer cells, is still trying to recognize some cell, and if it recognizes a cell which has got MHC1 normally expressed, it is inhibiting and doesn't kill it. But if it comes to cell which is, for example, tumor cell or virus infected cell, and which lost its MHC molecule, so this MHC molecule isn't here, NK cell is recognizing this situation and kills it. So it is natural, innate immune reaction against the tumor or virus infected cells. Unfortunately, usually insufficient, so it can be used at the beginning of infection, for example, but then the cell has to improve its ability to kill the infected cells by maturation of T lymphocytes. Monocytes, last white blood cells, are the biggest. They represent, their number is representing something between 2 to 10% of white blood cells. They measure up to 20 micrometers. They have the lightest nucleus amongst all leukocytes. The nucleus can be ovoid, kidney shaped, or lobated, but these lobes, this case is lobated, but these lobes are never connected by thin bridges. So lobation is not segmentation, it is something different. Cytoplasm of monocytes is basophilic, but they usually contain a lot of azurophilic granules, so it's never so homogeneous as we see in lymphocytes. And so the basophilia is combined with purple color of azurophilic granules, so the cytoplasm of monocytes is like bluish purple. Another example of lobated nucleus in monocyte, and electron micrograph showing quite high amount of euchromatin in the nucleus. Cytoplasm very rich in Azurophilic granules. They are labeled L because they in fact represent large lysosomal vesicles, lysosomal transport vesicles, Golgi complex, centriole, mitochondria, lot of ribosomes, mostly rough endoplasmic reticulum is here. Monocytes survive several days in blood, but then they leave the bloodstream as the other white blood cells, and in the tissue they transform into another cells. They transform into cells of so-called monocyte or macrophage system, or mononuclear phagocyte system. You already know some members of this system. You already know that when monocytes enters the connective tissue proper, it becomes macrophage. You also already know that when monocyte enters central nervous system, brain or spinal cord, it can become microglial cells. You also know, and I added it to this picture, then when monocytes enters bone, and in this case there have to be more monocytes in one place, they fuse together to form big multinucleated osteoclast. So this cell here is osteoclast, and it also belongs to the mononuclear phagocyte system. You didn't hear yet about dendritic cells. Dendritic cells belong to this system as well, and they are differentiating from monocytes which enter secondary lymphoid organs. So the result of this monocyte differentiation are another cells of this mononuclear phagocyte system, which are usually able to phagocytose or to resorb surrounding matrix, to digest it, to present it to lymphocytes. It is mostly the function of dendritic cells, but also macrophages. The last blood elements are platelets or thrombocytes. And as I said at the beginning, they are not full cells. They are not cells. They are only fragments, discoid fragments of cytoplasm of cells, which are called megakaryocytes and which are situated in bone marrow. They haven't got any nucleus, they have got only cytoplasm, and they have got some inclusions or organelles or cytoskeletal elements which they bring from the cytoplasm of megakaryocyte. Their size is quite variable, 2 to 5 micrometers, so they are the smallest formed blood elements, and simply said, they are important for blood clotting. The process of blood clotting or blood coagulation is quite complicated. You will study it in physiology and biochemistry, and one members of the complex of structures and chemicals important for blood clotting are blood platelets, which aggregate in the place where the wall of the vessel is damaged. They secrete some factors which are important for blood coagulation, and they start the blood clotting reaction. Here is a blood smear where quite many and quite large blood platelets are situated. You can see their variable size. Here is maybe the biggest. It can be like 5 micrometers. This neighboring is one of smaller, 2 micrometers usually. You can see that they are well stained. This is staining by azure, so they contain azurophilic granules. In the bigger platelets, we can see that this azurophilic staining is mostly in the center. Here down I can see this darker azurophilic staining is central and periphery is light blue. This central area of the platelet where granules are concentrated is called granulomere. Granulomere, it is the central area. And the peripheral light blue ring is called hyalomere. So in light microscope we can distinguish two parts of the platelet, granulomere and hyalomere, and it is possible only in the bigger platelets, not in the smallest. Sometimes platelets can be aggregated in groups, mostly in the situation when blood is clotting. If we look at the electron microscopic picture, or this is the schema redrawn from the electron micrograph, we can see that the platelet is supported by marginal microtubule bundle. There are microtubules which are very specifically arranged in one bundle surrounding the equatorial plane of the platelet, supporting and maintaining its special discoid shape. Then we can see three types of granules there. Greek letters are used for them. The biggest are alpha granules, smaller are delta granules or dense granules, dense bodies also, and the smallest are lambda granules, which are in fact lysosomal transport vesicles. So there are three types of granules. All of them are azurophilic. If you use electron microscope, delta granules are the densest, alpha granules are the biggest, lysosomes or lambda granules are the smallest. What else is inside? There can be sometimes mitochondria remaining from the megakaryocytes. There can be glycogen, frequently clusters of glycogen. And what is specific for platelets are two canalicular or tubular system. One is called open canalicular system. It is found on the periphery in the hyalomere of this platelet, and it is a system of deep and sometimes branched invaginations of the superficial plasma membrane. So they are important for the increase of surface, which is important for the contact of cells and for secretion of coagulation products, coagulation factors from granules. And there exists also dense tubular system, which is situated deeper in the granulomere. It is not probably connected with the surface and not much is known about it. Content of granules is variable. Lysosomes, it's clear, they contain lysosomal enzymes. They are important mostly for the terminal phase of clotting, when blood clot is released and the lysosomal enzymes can work here in the digestion of blood clot. Delta granules contain usually low molecular factors and also calcium ions, which are important for the coagulation. Alpha granules, they contain mostly proteins of coagulation. The main of them is fibrinogen, which doesn't exist only as a free plasma protein, but it is also concentrated in alpha granules, so its amount is increasing in the place where platelets are accumulating. Electron micrograph of the platelet can show the same structures as were visible on the schema. Microtubular bundle here, marginal bundle, so we can see to the section through the equatorial plane of the platelet. So here is microtubular bundle. Granules are here, probably the biggest. These are alpha granules, but it isn't easy to recognize them because all three types are dense. Glycogen is here. Open canalicular system, but unfortunately we don't see this connection with the surface because here is the marginal bundle which prevents the connection here, but in the neighboring platelet here down we can see it. Yes, it is invagination of the plasma membrane. Higher magnification of the periphery of platelet can show cross section, so it is opposite section than the previous picture. Cross section through the marginal bundle, you can recognize several microtubules in this area, and again granules, probably mostly alpha. Yes, and that's all. So this is the last picture. And okay, so it's dark here, so probably you don't see me. Nevertheless, thank you very much for the attention, and I am looking forward to see you here in the department. So goodbye.